Today we will be simulating the motion of objects caught in the gravitational pull of a black hole using Newton's second law. In the first part of this lab, we will estimate the mass of a black hole after being given the trajectory of the star that is orbiting it. In part 2, we will create a black hole for the orbit of a spaceship that will allow the object to still escape from the orbit of the black hole. The results from both of these parts are shown here. Newton's second law and the momentum principle will be key in predicting the motion of the objects here. We will estimate the gravitational forces using the universal gravitational force equation. Net force can be broken down into two components, a component parallel to motion and a component perpendicular to motion. The same is true for the change in momentum over time. It should also be noted that the net force equals the change in momentum over the change in time. The velocity and position update formulas will be needed to predict the position of the objects during motion. In the first part of the experiment, the system will only include the star. We will assume that the only force acting on the object is the gravity of the black hole, as there are no other objects around. This experiment is entirely computational, so we will only be using GlowScript. First, we will input the mass of the star and the change in the time interval, 1 day. Next, we will need to find the net force using the equation Fnet equals the change in momentum over the change in time. Since we have the initial and final velocity, this can be done using these equations. Once we have the net force, we can equate Fnet to dp over dt. The direction of the initial momentum is the same as the parallel direction of motion, so we can find the parallel component by multiplying dp over dt by the direction of parallel motion. Since the two components of dp over dt add to make the whole value, we can rearrange this equation to find the perpendicular component of the force. The perpendicular and parallel components of force are equivalent to the corresponding components of change in motion. Finally, we can obtain the mass of the black hole by rearranging the universal gravitational force equation. Since we will obtain a mass of the black hole each iteration of the calculation, we must take an average of these masses, which is reported here. The system in part 2 only includes the rocket. The ship will start with some initial velocity, and then the only forces acting on it will be the gravitational forces of the star and the black hole. After inputting the mass of the black hole, we must calculate the net force on both the ship and the star using the universal gravitational formula. We will then simulate the motion of both objects using the position and velocity update formulas. The initial velocity to create a partial orbit that allows the object to escape the system was obtained from trial and error. Note that the speed is less than the speed of light, so this is theoretically possible. Although this is theoretically possible, the physics of the actual scenario may be a little more complex as we don't account for everything such as drag forces. What if the rocket was trying to enter orbit with a black hole instead of trying to escape the orbit? This would require a lower velocity in the x direction, leading to a lower speed overall. Once again, this velocity was found from trial and error. Finally, what does it all mean? What's the difference between the change in momentum and the net force? The net force is a measure of the agents acting on an object attempting to change the motion. The change in momentum is a measure in the change of an object's motion. These values are equivalent to each other, but they are not the same thing. That's about it. See ya.